This is section 9.5 of Honors Algebra 2, Hyperbolas, the fourth of our four conic sections. We've had circles, parabolas, and ellipses. Now, hyperbolas. A hyperbola, by definition, is the set of all points P in the plane such that the difference between the distances from P to two fixed points is a given constant. If I change this to the sum between the distances from two fixed points is a constant, then I'd have an ellipse. Now I've got the difference. So I'm going to take two fixed points. I'm going to take another point such that the difference between the two distances I form with my two fixed points is a constant. So I'll take the two distances and I will subtract them. And I want that to be the same number every time. Each of the fixed points is a focus. So a hyperbola has two foci, just like an ellipse. The fixed distance is called the focal radii. Hyperbolas are curves with two branches that are identical in shape. You'll get the sense of what I mean by that as we graph them later. How do I find the equation of a hyperbola? Well, if my two foci, let's say, are negative 5, 0 and 5, 0, and the difference of focal radii is 6. So, negative 5, 0 and 5, 0, and a difference of focal radii of 6. It means I want all the points whose difference of distances from those two foci is always 6. Okay? So let's take P, call it x comma y. That's my P. And let's say that that is a point on the hyperbola. Well, what needs to be true? Well, it needs to be the case that if I take the distance from P to F1, which would be this, if I take that distance, because that's F1 down there, minus the distance from P to F2, which is that distance, if I take those two distances and subtract them, I should get 6. Now, it shouldn't matter which order I subtract them in, as long as I take the absolute value. Okay, so if I take PF1 minus PF2 and take the absolute value, that needs to be 6. Because I don't know necessarily which one is longer, because P could be anywhere in my hyperbola. So in other words, if I have an absolute value equation equal to a positive number, how do I get rid of that absolute value? Well, you remember, of course, from last semester, an absolute value equation equal to a positive number means I have two equations. One with a positive number, one with a negative number. So PF1 minus PF2 equals plus or minus 6. So let's apply, just like we did with circles and parabolas and ellipses, let's apply the distance formula for each of those two distances. So the distance from P to F1 is going to be the square root of, well, x minus negative 5, which is plus 5, quantity squared, plus y minus 0, which is y squared. And then subtract the distance from P to F2. Okay? Well, that's the square root of x minus positive 5, quantity squared, plus y minus 0, so y squared. That needs to equal plus or minus 6. So then, simplifying to 16x squared minus 9y squared equals 144. And then we will divide both sides by 144 so that, like with an ellipse, we have this equal to 1. And so that reduces to x squared over 9 minus y squared over 16 equals 1. And that's the equation of my hyperbola. Did you keep up with that? No? That's all right. You don't need to know that. Because now we will use that to come up with a formula. But first, let's graph this. Notice that our equation x squared over 9 minus y squared over 16 equals 1 is of the form x squared over a squared minus y squared over b squared equals 1. Okay, so we've got a's and b's like we did with ellipses. The difference is, here, there's a minus in the middle. The ellipsis had a plus. That's the key. Now let's graph our hyperbola. Are there intercepts? Well, if x is 0, what is y? If x is 0, we just get negative y squared over 16 equals 1, which means negative y squared equals 16. So y would equal the square root, plus or minus the square root of negative 16. Those are going to be imaginary numbers, which we'll not be able to graph on our graph. So there are no y-intercepts. What about x-intercepts? If y is 0, then we've got x squared over 9 equals 1, which means x squared equals 9, so x equals plus or minus 3. I've got two x-intercepts. One at 3, 0. One at negative 3, 0. Very good. What is the extent of my graph? So if I were to take it, and let's say I were to solve it for y, I'd have y equals plus or minus 4/3 times the square root of x squared minus 9. Y will be a real number only when x is bigger than 3 or lower than negative 3. Because if x is between negative 3 and 3, I will have a negative number underneath my square root, and I can't have that. So x needs to be bigger than positive 3 and or lower than negative 3. So I am trapped beyond, to the right of positive 3, to the left of negative 3. If I were to solve my equation for x, I'd have x equals plus or minus 3/4 times the square root of y squared y squared plus 16. Which means that I can get any value I want for y, because y squared plus 16 will always be a positive number. So x is bounded, y is not. That's useful to know in my graph. And do I have symmetry? Well, I will have symmetry. I will be symmetric with the x-axis. I will be symmetric with the y-axis. And it turns out in this case I will also be symmetric with the origin, with 0, 0. Notice that if I were to take my equation here, y equals plus or minus 4/3 square root of x squared minus 9, I can, if I wanted to, rearrange it in a funky way by taking x squared out of x squared minus 9, so that's 1 minus 9x squared. If I divide x squared minus 9 by x squared, I get 1 minus 9 over x squared. That way I can take the square root of x squared and get x. The whole point of that is to see that if I were to let x be really, really big, then I'd be taking 9 divided by a really, really big number, which is essentially 0. And so I'd have 1 minus 0 underneath that square root, which is really essentially 1. And I'd have the square root of essentially 1, which is essentially 1. So I'd have y equals plus or minus 4/3 x when x is super big. So as x approaches infinity. That means that as I keep going further and further to the right on my graph, or further and further to the left of my graph, if x is super, super negative, the same thing will happen, then my graph approaches these lines of positive 4/3 x and negative 4/3 x. Those are lines with slopes of positive 4/3 and negative 4/3, and y-intercepts of 0. So if I were to graph those lines like this, and I'll graph them as dotted lines because they're not actually part of my hyperbola. So that's y equals 4/3 x. It's a slope of 4/3 going through the y-intercept of 0. Same thing over here. That is y equals negative 4/3 x. My graph is going to be trapped by those lines, and it's going to get closer and closer to them as x gets further and further positive and further negative. Okay? Those are called asymptotes. A-S-Y-M-P-T-O-T-E-S. I have two asymptotes on my hyperbola. Okay? My hyperbola then will look like this. It's going to approach the asymptotes. And I could plot more points, but for the sake of time in this video, I'm just going to sketch it like that. The center of a hyperbola is the midpoint of the line segment that joins its foci. So notice my foci here, we're at 5 and negative 5. The center of the line segment that joins those is 0, 0. So the center of my hyperbola is 0, 0. Notice that is not actually on my hyperbola. Our hyperbola above has a center of 0, 0. That should not surprise us looking at the equation where there's just x squared over 9 minus y squared over 16 equals 1. We don't have x minus or plus a number or y minus or plus a number. We will call the line containing the center and foci the major axis. So in our graph we just did, the x-axis is the major axis. If the x term is positive, the major axis is horizontal, and so is the hyperbola. So we had that because we had x squared over 9 minus y squared over 16 equals 1. So our x term was positive, our y term was negative. So if the x term is positive, the major axis is horizontal, and so is my hyperbola. It opens left and right. If the y term is positive, so if it was switched, y squared over 16 minus x squared over 9, that still gives me a hyperbola, but it's one where the major axis is vertical, so my hyperbola opens up and down. We'll call the distance from the center to each focus c, just like we do with an ellipse. The difference of focal radii equals 2a, just like with an ellipse, to the hyperbola along the major axis. So a, in this case, was 3. The distance from the center to the hyperbola along the major axis. So notice our equation was x squared over 9, which is x squared over 3 squared. That's a squared. We will define b such that b squared equals c squared minus a squared. And if we were to do that here, we would see that b would be 4, and that gives us the 4 squared underneath the y. Okay. So what about hyperbolas whose center is not at 0, 0? So here are the formulas for hyperbolas with the center at hk. And anytime we want to find the equation of a hyperbola from now on, we will apply these formulas. We will not go back to the distance formula. That's why I sped through that example earlier. If we have a horizontal major axis, notice the x term is positive, and a squared is underneath that, and the y term is negative, and b squared is underneath that. And then the foci, or distance of c, away from the center horizontally, to the left of the center and to the right of the center. And then there's the equation of the asymptotes in point-slope form. If we have a vertical major axis, squared underneath that, minus the x term, which is negative, and a b squared underneath that. So the a is always underneath the positive term, the b is always underneath the negative term. The foci this time are a distance of c vertically away from the center, so add it to k and subtract it from k. And there's the equation of the asymptotes. The only difference is that the slope is the reciprocal. In either case, c squared equals a squared plus b squared. That's our situation for a hyperbola. Notice that's a little bit different than for an ellipse. So let's try 2 examples. Number 1, graph the hyperbola y squared equals 3x squared plus 12. All right, well, let's put that in the form that we want it in. So let's get the x squared and y squared on the same side. Y squared minus y squared minus 3x squared equals 12. We divide by 12 because we want a 1 on the right-hand side. That gives us y squared over 12 minus x squared over 4 equals 1. So that means a equals the square root of 12, which would be 2 radical 3, and b equals 2. C squared, which remember is a squared plus b squared. C squared would be 12 plus 4. C squared is 16, which makes c equal to 4. Okay? My center is at 0, 0. This is going to have to be a vertical hyperbola because the y squared, the y term is positive. So I'm going to go up a distance of c to get my focus and down a distance of c to get my other focus. So its foci are going to be 0, 4 and 0, negative 4. But those are not on the hyperbola, those are inside of the branches of the hyperbola. To get the hyperbola, I'm going to go up a distance of a and down a distance of a. So if I go up a, that's square root of 12, and the square root of 12 is about 3.5. So I'm going to go up about 3.5 and down about 3.5. Those are going to be the points on my hyperbola. And the asymptotes are going to be plus or minus 2 radical 3 over 2 times x. So y equals plus or minus radical 3x. All right. Radical 3, about 1.73. So just a rough sketch of my asymptotes put me somewhere around there. I'm speeding up for the sake of time in the video. And my hyperbola will look something like that. Again, I should be more exact, but I don't think you'll mind me speeding through this. Right? Okay, cool. Number 2, find an equation of the hyperbola having foci -3, -2, and -3, 8, and a difference of focal radii of 8. Okay, so I've got the foci. I need to use those to find the center so that I can come up with the equation. And then we need to find a squared and b squared. Okay, so let's just make a quick sketch here. -3, -2 puts me there. -3, -8, -3, positive 8 puts me up there. Halfway between the foci is going to be the center. Well, it's halfway between -3, 8 and -3, -2. Well, that looks like -3, 3, which is a distance of 5 away from both of those. So my C is 5. Okay. My center is at -3, 3. That's my HK. HK equals -3, 3. C is 5.
Shane Lobster, please report to Mr. Kelly in the middle school. Shane Lobster to Mr. Kelly in the middle school.
The difference of focal radii, remember, is 2a. So 2a equals 8. A then equals 4. So I know c squared equals a squared plus b squared, where c squared is 25, a squared is 16. We're going to add that to get b squared, or add b squared to that. So 25 minus 16 is 9. 9 equals b squared. That means b equals 3. Okay? Now I've got enough to find my equation. I'll have, since this is going to have to open up because the major axis is vertical, we'll have the y term positive. And so that will be y minus 3 quantity squared over, it's always over a squared. The positive term is always over a squared. So that's 16 minus x minus -3, so x plus 3 quantity squared, over b squared, which would be 9, and that equals 1. That's my equation. And here are your immediate practice problems. Number 1, graph 16x squared equals 9y squared plus 144, showing the asymptotes as dotted lines and find its foci. Number 2, find an equation of the hyperbola having foci at 0, 3, and 0, -3, and a difference of focal radii equal to 2. That is the end of section 9.5.